So earlier in the course, we saw indeterminate forms when we were taking limits. And these came up in certain ways. 0 over 0, infinities over infinity, 0 times infinity, 1 to the infinity, 0 to 0, infinity minus infinity. And so we saw some ways that we could work with these provided certain things happen algebraically. A common factor we were able to remove, or certain other situations we learned how to deal with. But there's another rule that allows us to evaluate these limits that yield indeterminate forms. It's called L'Hopital's rule. It's a French name, so it's a little tricky to pronounce maybe if you don't know any French. And basically what it says is, if we have certain indeterminate forms, if we have the limit as x approaches a of f of x over g of x giving 0 over 0, or the limit as x approaching a of f of x over g of x giving an infinity over infinity, where a is any real number, infinity or negative infinity, so we can be taking the limit at any value, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. It's a very powerful tool in taking limits. So now we're going to see some examples of how we can use this new tool, L'Hopital's rule. So let's evaluate the limit with x approaching 0 of sine x divided by x. Now, if you remember, this limit was very difficult to evaluate when we first learned about it. We had to create a geometric argument and use the squeeze rule, or the squeeze theorem, to evaluate this limit. It was very difficult. It took us maybe 10 minutes to evaluate this one limit. Okay, so if we try a direct substitution, limit as x approaches 0 of sine x over x, a direct substitution gives us a 0 over 0, an indeterminate form. So we can't evaluate this directly right now. However, if we apply L'Hopital's rule, so let's remove this, and instead let's apply L'Hopital's rule. And so a notation that has come into fashion for applying this rule is to write a little h above the equal sign. So now I'm applying L'Hopital's rule here, and so this becomes then the limit with x approaching 0 of, instead of sine x, the derivative of sine x is cosine x, and instead of x, the derivative of x is 1, with respect to x, of course. So then this is just the limit as x approaches 0 of cosine x. As x approaches 0, cosine x approaches 1, and 1 is constant, so that's 1. And so this limit is 1, which is the same result that we got earlier with the geometric argument and the squeeze theorem. The method works. And we won't prove that the proof of the theorem is well beyond the scope of this course, but we will use the theorem. So here's another example. Let's find the limit as x approaches 1 of x squared plus 8x minus 9 over x cubed minus 2x squared minus 5x plus 6. Quick substitution. If we just were to try letting x equal 1, that would give us 1 plus 8 minus 9, that's 0. So that's a 0 in the numerator. 1 minus 2 minus 5 plus 6. That's negative 6 plus 6 is also 0. So this is a 0 over 0 situation again. We apply L'Hopital's rule. So then this becomes the limit with x approaching 0 of 2x plus 8 over 3x squared minus 4x minus 5. Now, letting x approach 0, that would give us, x should not be approaching 0, x should be approaching 1. Sorry about that. Then that would give us 10 over 3 minus 4 is negative 1 minus 5 is negative 6, negative 5 thirds. All right, so both of these situations, if we try to direct substitution, we got a 0 over 0 indeterminate form. We apply L'Hopital's rule and go from there. Let's see some more examples. Let's find the limit as x approaches negative infinity of e to the negative 5x over 7 plus e to the negative 2x. All right, so let's see. E to the negative 5x. E to the negative 5x, remember, that would be a decreasing function. E to the negative 5x would look roughly like this. And so as x approaches negative infinity, e to the negative 5x would go to infinity. So direct substitution would give me an infinity in the numerator. And similarly, e to the negative 2x is going to have a similar graph. It's again going to be a decreasing exponential function. So as x approaches negative infinity, e to the negative infinity goes to, as x approaches negative infinity, e to the negative 2x goes to positive infinity. The 7 is inconsequential in that situation. And so we have an infinity over infinity indeterminate form. All right, applying L'Hopital's rule. This becomes the limit as x approaches negative infinity of negative 5 e to the negative 5x over negative 2 e to the negative 2x. All right, remembering our rules for limits, I can bring the negative 5 halves. That would not be negative because a negative divided by a negative is positive. So I'd have 5 halves, limit, with x approaching negative infinity, and e to the negative 5x divided by e to the negative 2x would be e to the negative 3x. So as x approaches negative infinity, e to the negative 3x would approach infinity. 5 halves times infinity is infinite. Okay, so in this situation, we didn't end up with a real number as the limit. It ended up being an infinite limit. That's okay. We were still able to apply L'Hopital's rule to come to that conclusion. Now would be a good time to pause. Try this next one on your own. All right, well, did you pause? Did you try it? So here's how I would see this. Let's see, natural log x. All right, if we think of a quick sketch in natural log x, it does that roughly. And so as x approaches infinity, the natural log x keeps increasing. And so natural log x would go to infinity. X squared would also go to infinity as x approaches infinity. So again, this is an indeterminate form, the infinity over infinity case. Let's apply L'Hopital's rule. So then this becomes the limit with x approaching infinity. The derivative of natural log x is 1 over x. And let's see, x squared, the derivative of x squared goes to 2x. And so I can simplify this. This becomes the limit as x approaches infinity. I can take the 1/2 outside if I really wanted to. Doesn't matter too much. But after simplifying, this becomes 1 over 2x squared. And so as x approaches infinity, the x squared goes to infinity. 1 over infinity. This is no longer an indeterminate form. 1 divided by infinity goes to 0. This limit is 0. So remember, L'Hopital's rule only applies if we have an indeterminate form. 1 divided by infinity is not indeterminate. And so we can apply what we learned in the past. This would be another good time to pause and try this one out on your own. Find the limit as x approaches 0 from the right of sine x over natural log x. Alright, as x approaches 0 from the right, the sine x goes to 0, right? The sine of x would go to 0. What about the natural log of x? Let's remember that graph of the natural log function that I just sketched on, I think, the previous slide. It does something like this. And as x approaches 0 from the right, the natural log of x goes to negative infinity. 0 over negative infinity. This is not an indeterminate form. We would not apply L'Hopital's rule. And if we did, we would get an incorrect result. So be careful. Now that we have this rule, that doesn't mean we apply it every single time. We only apply it if it's an indeterminate form of 0 over 0 or infinity over infinity. So this limit ends up being 0. 0 divided by an infinite number, any real number, divided by an infinite number is 0. All right, let's look at a couple more situations now. So here we're asked to evaluate the limit with x approaching negative infinity of x squared times e to the x. All right, so as x approaches negative infinity, x squared, this term would go to infinity, and e to the x as x approaches negative infinity. So remember the graph of e to the x does something like this, and so as x approaches negative infinity, e to the x goes to 0. So I have an infinity times 0. This is an indeterminate form. All right, so, but we can't apply L'Hopital's rule to it. We can only apply L'Hopital's rule if we have a 0 over 0 or an infinity over infinity. So we have to adjust this limit a little bit. So we use a little bit of algebra. This is the same as the limit with x approaching negative infinity. And I will write this as x squared over e to the negative x. This is algebraically equivalent to the original expression, but now this gives me an infinity in the numerator, and e to the negative x as x approaches negative infinity. Right now, e to the negative x looks like this. Right, there's e to the negative x. As x approaches negative infinity, e to the negative x goes to infinity. So this gives me an infinity over infinity, and now I can apply L'Hopital's rule. So this becomes the limit as x approaches negative infinity of 2x over negative e to the negative x. Now, as x approaches negative infinity, 2x is going to go to negative infinity. Negative e to the negative x, that's going to be, again, an infinity of some type. All right, so this is going to give me a negative infinity in the numerator. This is going to give me a negative infinity in the denominator. I can apply L'Hopital's rule again. So this becomes then the limit with x approaching negative infinity. 2x, the derivative goes to 2. Negative e to the negative x, the derivative goes to e to the negative x. Now I have 2 over infinity, and that is no longer an indeterminate form. 2 over infinity goes to 0. So in this situation, we had to apply L'Hopital's rule multiple times, but again, only if we had an indeterminate form at each step, either a 0 over 0 or an infinity over infinity. Let's look at this next example. The limit with x approaching infinity of x times the sine of 7 over x. As x approaches infinity, well, x would approach infinity. 7 over x would go to 0, and the sine of 0 would be 0. So again, this is an indeterminate form of the form infinity times 0. All right, so now, why don't you try and take it from here and see if you can evaluate this limit. All right, so what I would do is I would rewrite this as the limit with x approaching infinity, and I will write this as sine of 7 over x over 1 over x. That's algebraically equivalent to the original expression, and now as x approaches infinity, this gives me a 0 over 0 situation, and I can now apply L'Hopital's rule. So then this becomes the limit with x approaching infinity sine of 7 over x. The derivative is cosine of 7 over x. Then by the chain rule, I would have a negative 7 over x squared. Right, the derivative 7 over x, that's 7x to the negative first, so negative 7 over x squared. Similarly in the denominator, this becomes a negative 1 over x squared. So now, using some algebraic simplifications before I substitute, the negative 7 over x squared divided by negative 1 over x squared, that's just positive 7. Let's bring that 7 outside the limit. So this is 7 times the limit as x approaches infinity of the cosine of 7 over x. And as x approaches infinity, this becomes the cosine of 0. So that's 7 times 1, which is 7. All right, let's consider one more example here. We are asked to find the limit as t approaches 0 on the right of e to the t plus t to the 1 over t. All right, so if we had tried a direct substitution, e to the 0 goes to 1. T would go to 0, so that's 1 plus 0. And 1 over t, as t approaches 0 from the right, 1 over t would go to positive infinity. So I have a 1 to the infinity. This is another one of our indeterminate forms. And we can't directly apply L'Hopital's rule, though, because it's not in the right form. It's not a 0 over 0 or an infinity over infinity. So we're going to have to do some algebraic manipulations to this one. All right, so I'm going to start a little differently for this one. I'm going to start by saying let y equal this limit. And what I'm going to do is a trick we've seen before. I've got to do something with this exponent. This exponent's causing issues. So I'm going to algebraically manipulate this to get rid of an exponent. And to do that, I will apply the natural log to both sides of this equation. So the natural log of y is equal to the natural log of the limit as t approaches 0 from the right of e to the t plus 1 to the 1 over t. E to the t plus t. E to the t plus t. Not e to the t plus 1. All right. Now, our rules for limits allow me to bring the natural log inside the limit. So this then becomes the limit with t approaching 0 on the right of the natural log of e to the t plus t to the 1 over t. Now, I can use my rules for logarithms. The natural log of e to the t plus t to the 1 over t, that's the same as the limit, t is approaching 0 on the right, of 1 over t times the natural log of e to the t plus t. Or the limit with t approaching 0 on the right of the natural log of e to the t plus t over t. And so now if we look at this limit on the right, e to the t plus t, as t goes to 0, this then becomes the natural log, the numerator becomes the natural log of 1, which goes to 0, and t, as t goes to 0 on the right, this goes to 0. So I now have an indeterminate form of the form 0 over 0, and I can apply L'Hopital's rule. So then the natural log of y, remember that was the left-hand side, the natural log of y is then applying L'Hopital's rule. is the limit with t approaching 0 on the right. The derivative of the top, natural log of e to the t plus t. So that would be 1 over e to the t plus t. Oops, sorry about that. Times the derivative of e to the t plus t is e to the t plus 1. And then in the denominator, this just becomes a 1, right? The derivative of t is 1. So then the natural log of y becomes the limit as t approaches 0 on the right. And this is just then e to the t plus 1 over e to the t plus t. Now, letting t approach 0 on the right, this becomes e to the 0 becomes 1. So this is 1 plus 1 over 1 plus 0. So the natural log of y is 2 over 1, which is 2, which means that y is e squared. And so this limit is e squared. So these situations where we have either 1 to infinity or 0 to the 0, you're going to have to use this sort of method where we apply the natural log on both sides, use some algebraic manipulations before we apply L'Hopital's rule. These can get a little tricky. Alright, so that's the basics of how to use L'Hopital's rule to evaluate limits if they're indeterminate forms. So now it's up to you to get some practice.